Welcome back, everybody. So let's continue from where we were. So you see, it's a nice example of when you learn something in a theoretical course, like theoretical computer science or algorithms and data structure, and then you see it in use in real life for building real systems. And that's true for a lot of things you learn in theoretical computer science. That gives you the theoretical foundation for making things much more efficient in existing products. So I told you at that point we have the binary trees, binary search trees to be more exact, where we have these values on the non-terminal nodes that help us find the postings, the terms we are looking for. And then all the leaves point to the postings lists. And we can do it in logarithmic time. Now that's an example of a binary search tree with actual terms where if I'm looking for should now, that's actually, I built the structure with the example we had before. And then you start here. And then with a logarithmic number of comparisons, you can locate, is it left, is it right? You can locate it, right? That was with the prior convention that the terms are everywhere, right? There's really two conventions. There's the convention like here, that the terms are everywhere in the tree. That's convention number one, and convention number two, that the terms are only on the leaves, right? So that was with convention number one, and here you locate this in algorithmic complexity. Very good, but that's not it. Because a binary search tree is not efficient enough, and that has to do with the way that we read and write from the disk. You know that you can read with random access from your hard drive, right? You can locate any bytes that you want to read, you can read them from the disk. But you might know that when you do that, you do not read just the bytes you want, you read full blocks, roughly 4,000 bytes. Who knew that? Who didn't know that? Ah, okay, then I'm telling you, okay, so that's good, so you learned something. So we never read single bits or single bytes from the hard drive. We always read and write blocks, and the blocks are typically 4,000 bytes, 4 kilobytes, right? And so that's the only thing we can do. So if you want to read a couple of bits, you still have to read an entire block. Now imagine that this index right here can go very big. If we have a very large collection or you index the whole internet, you might not be able to fit it in your memory, in your RAM of your machine. So you might need to store some of it on the drive. And so it might be that when you actually look up what you're looking for, you end up reading from the disk these things. The problem is that if you go like this down here, and you end up reading from the disk, you might need to only read that from the disk, perhaps, or even that, right? This group here. The problem is that might be much smaller than 4 kilobytes. So you're basically wasting your resources because you're reading and writing from the disk very small chunks that will force reading an entire block for nothing. And so that is the reason why in database systems and information retrieval systems, people do not use binary search trees because that would be a waste of resources. Instead, they expand the nodes, they allow for more children, and ideally, that should be sized in such a way that gives you a disk block in terms of reading and writing. And then you're efficiently using the disk resources. For whom is that clear? Right, very good. Okay. So again, this is because disks are accessed with full blocks at a time. So that's an example of a structure with more children per nodes. Please pardon me the formatting that has to do with what I told you about importing the slides into this new system that we're trying right now, and it's not entirely smooth yet. So I hope it doesn't disturb you too much. But this is pure cosmetics. So this structure here that allows for more than 2 children is called a B tree. And then there's the plus, and I will explain what the plus is. But basically, B tree means you can have more children than the 2. Plus means that you use convention number 2, meaning that the terms are at the leaves. And on the other nodes, the non-terminal nodes, these are just values for searching, but the terms are at the leaves. When that is the case, that is called a B plus tree, right? So you recognize the B plus tree because you have the terms that are right here, and the terms that you have here are only for looking them up, right? But they are not linked to any postings list. This is called the B plus tree. Now, B plus trees are not just about allowing more children. There's a bit more than that. I have to warn you that there is not a single universal definition of B plus tree that everybody agrees on. So if you try to Google for it or go to Wikipedia or open books and so on, you will find that it's a huge mess. There are so many different conventions about how to do it. The principle is kind of here, but the exact conventions might differ. So for this course, I'm going to give you the conventions we have, but just be prepared that if you read textbooks or look somewhere else, you might see some different conventions, and that's okay. So one first constraint of a B plus tree, and of a B tree, in fact, is that all leaves must have the same depth, right? All leaves at the same depth. You cannot have some leaves at depth 4 and some leaves at depth 5. Here, they are all at depth 2, the leaves. That's condition number 1. So you see it's very nicely balanced and very nice visually. And then number 2. Constraint number 2 is that we don't allow any number of children. We allow an interval of number of children. That interval is configurable. You can tweak it, you can change it, you can parameterize it, and obviously we want to parameterize it in such a way that it fits with the disk block size, as I said. But very roughly, that interval is about a number and double that number, very roughly, and this is where there's multiple conventions. But very roughly, the upper bound is very roughly double the lower bound. And that gives you the allowed number of children in the tree, right? So you see here, we have 4 children and 3 values in between, right? Everything that is smaller than this value is the first child. In between these 2 values, that's the second child. In between the second and third value is the third child. And greater than the third value is the fourth child. And here we again have 4. So between 3 and 5 children. Between 3 and 5, there's no raised hand or anything, nobody complains. Between 3 and 5 children. No complaints? What about the root? It has only 2 children, and yet that tree is fine. Well, that's because the root is an exception, and that's the only exception you can have is the root. The root is allowed to have less than the lower bound. That's the only exception. So if the root has less than 3, then this is fine. It can have 2. 1 would be useless, of course. If the root has only 1 child, then you can just get rid of it, right? So it's okay if the root has between 2 and 5 children. But again, that's the only exception. Everywhere else, it has between 3 and 5 children. Who is with me? All right. And it's fine if the root has less. Actual terms only at the leaves, that's the plus, B plus tree, means that, and so I use the color blue in order to make that very clear. Now, when we parameterize such trees, we like to use these 2 values, the lower bound and the upper bound, as a prefix, meaning that this here would be a 3-5 B plus tree, because I have this 3 and 5 interval. So that's a 3-5 B plus tree. This here is a 2-4 B tree. Not plus, because now we have terms everywhere. So that's why not plus. It's just a B tree. And 2-4, because the number of children is somewhere between 2 and 4. And if you look, you have 4 children, 2 children, 2 children, 3 children. That's all within the bounds, right? So this is a 2-4 B tree. Who agrees? right? Okay, so 3, 5, B plus 3, 2, 4, B3, and so on. Now, the B plus trees, plus sounds cool, right? It's like when you have these video on demand offerings like Disney Plus and so on. Now it's Max. Max is the new Plus. But basically, it means that there's extra features in B plus tree. It's like the premium version of the B tree. And one of the premium features that we get in a B plus tree is that since all the terms are at the leaves, we can build here an efficient structure that traverses left to right the entire list of terms. All we need is extra pointers. In fact, this is just a simply linked list. It's a list, an additional structure in addition to the tree, in top of the tree, that connects all of the leaf nodes as a singly linked list. Who sees that? Right. With that list, I have this super fast way of traversing the entire set of terms. If I want to scan through it, I can do it efficiently. I don't even need to look at the rest of the tree. I just start in here and then I traverse it efficiently. Obviously, in practice, we'll see that we don't need to traverse it completely, but at least we can traverse intervals of terms. And I will come back, maybe even today, of why that is actually a useful feature. All right, so that is the plus in B plus tree, premium feature. We have this linked list, this singly linked list of connecting all of the leaves and giving us access in linear time to the entire list of terms, alphabetically sorted, because that's the beauty of having a structure like this. Now, when I said 3, 5, that was a bit arbitrary, right? And the idea is that the parameter you vary, let's call it D, that gives you intervals between D plus 1 and 2D plus 1. And D can be anything. So when I said 3, 5, D was basically 2, right? If you plug in here D equals 2, then you get 2 plus 1, 3, 2 times 2 plus 1, 5. So that means you have 3, 5, but you also have 1, 1, 2, 3, 3, 5, 4, 7, 5, 9, 6, 11, and so on, right? Of course, the low values are only useful for pedagogical purposes and for teaching, because in practice, it's not going to be such small values, right? We are going to have larger values in order to match the disk block, right? But for my slides, I'm picking small numbers, okay? And so that gives us a convention on the number of children. And the reason I warned you about Wikipedia and textbooks and so on is that not everybody uses that convention. There are people who might be using D2D or D plus 1 2D or variations of that. Just to keep your sanity, I'm just giving you that one, and that's the one we use here. But just be aware that you might find other conventions elsewhere. And it doesn't really matter. I mean, in the end, it just works, whatever the convention you use. Now, a bit of warning. I have how many trees here? 1, 2, 3, 4, 5, 6, 7, right? So I have 7 trees. That would be my subtrees at a certain node. 7 trees. How many intervals do I have? Who thinks 7? Who thinks 6? And it's 6, right? It's 1 less than the number of trees, right? So if we have 7 trees, we have 6 intervals. So 1 less. So it means, and you probably already noticed it here, that when I say I have 4 children here, I have 1 less value here. I have 3 values, right? If I have 2 children here, I have 1 value, right? So it means that I have to pay attention if I'm talking about intervals of numbers of children or intervals of number of values per node. If I'm saying I have between 3 and 5 children, who agrees I have between 2 and 4 values? Who agrees with that? Right? Just something to be careful about. That can be a source of confusion. Always keep that in mind. And saying that is important because it means that when I say between 3 and 5 children, meaning between 2 and 4 values, that interval between 2 and 4 values also applies to the leaves. So when I'm saying I have a 3, 5 B plus tree, that also means that the number of values in a leaf has to be between 2 and 4. Right? Just this offset of 1 because we're talking about the values and not the number of children. For whom is that clear? Right? Very good. Very good. So indeed, 1 less interval. So 2 keys mean 3 children, 3 keys, 4 children, 4 keys, 5 children. I call it key, value, you know, it doesn't matter what we call it. I said a lot value. Some people call them keys because you look up something, right? So when you look something up, you can also call them keys because they help you look up. But anyway, that's the number of intervals, 1 less than the number of children. All right, so if I say now the number of children between d plus 1 and 2d plus 1, that means that the number of values per node or keys is between d and 2d. Okay, so that is the convention that we have here. And now I have an animation for you. We could have asked you to build a B plus tree as an exercise. The problem, and that's a practical thing that, sadly is so, it is in fact complex to build a B plus tree. There are so many moving features and bells and whistles and so on that it can get very, very quickly, very complex. Also because of all the number of conventions that there are. There's a lot of degrees of freedoms in which you can do that. Also the insertion algorithm, deletion algorithm, because there are algorithms on how you insert a new value in the tree, how you remove a value in the tree, is also not trivial. So we are not going to ask you to implement it. I will just show you an animation, just so you get a feeling of what it looks like when you insert things. I will take a specific insertion pattern, which doesn't have always to be that pattern. I'm just going to insert increasing integers, 1, 2, 3, 4, 5, and so on. These integers, of course, would be terms in the context of information retrieval, but let me just use integers. So let me insert the value 1. We built the structure. We built the B plus tree, and I build it from my vocabulary. So that's easy, right? I just insert 1. It was empty. Now there is 1. So now we have a B plus tree with just 1 single node, the root, and the value 1. And if I want to insert another value, then I can just insert it also in the root because there are not so many yet, right? Now 3. I continue to insert. But as you guess, it's not going to go like this forever, right? Because we put a limit at some point. And we are going to limit the number of keys with the same convention I told you. We have a 3, 5 B plus 3, and so that means that the number of keys is between 2 and 4. So for the root, it cannot be higher than 4. So with this assumption in mind that my maximum number of values is 4, I just broke the rule. I tried to add 5, and now 5 is just too much. So what do I do? What do I do to fix this? I just split it, right? Just cut it like this with 1, 2, 3 on the left, 4, 5 on the right, and I turn them into children of a new root. And then I put the 4, and the 4 is just the smallest from the right, right? So everything on the left is strictly less than 4. Everything on the right is greater than or equal to 4. And now you see, and this is why this lower bound and upper bound has to be taken simple to double, like d plus 1, 2d plus 1, because now that we had this 2d plus 1 that is too much, if we split the 2d plus 1, we can split it into d plus 1 and d, right? And now d plus 1 and d, that is within the interval that we want. In that case, we have 3 and 2, and that is within the interval 2, 4, right? Who gets that? Right? So since we have these bounds, we can always split it in this way when it's just 1 too much, and that brings us back into 2 intervals that are acceptable for our parameters. And then I continue to insert. That's still okay. That's still okay. That's not okay. Now I have 5 in here. So now I split again this one in 2 parts. I can use 7 as the pivot. And then all I need to do is add the 7. There's still room on the root, right? So I can add a second value on the root now, and it has 3 children, right? Then I continue to add 9, 10. That's still okay. 11. Now we are breaking again the upper bound. We have to have at most 4 values. So we break it again. And now we have 3 values on the root, which means 4 children, right? So now I just fast forward because we can go on like this for a while. So let me fast forward to 16, where there was also a bit of rebalancing that we moved over a few things. And 17 comes, which forces us to split again. But now you see something new is happening. Not only do we break the rule here, now it propagates to breaking a rule somewhere else. So what do? We split it again, and that's how we increase the height of the tree. Now we get a tree of height 2, right? And it just goes on and on and on and on and on like that, right? So this is what it looks like when you build a B plus tree. Now again, I took the specific case where the terms arrive sorted. In reality, that might not be the case. You might have the terms arriving in random order because this is the order in which you are reading them, right? And then the algorithm tells you how to insert, and when you insert, if we break a rule, how to split the nodes. Who has an intuition now behind B plus trees? Awesome. So that was a 3-5 B plus trees, B plus tree. And if you delete, it's the same intuition, you just delete, but then the rule you might break is the lower bound, right? You might at some point have not enough values. And again, the root is the exception, but that's not the root here. So it's not the root, so what do? We merge like this. But now we break that other rule, so we merge again and so on. So that's now how the tree shrinks. So you see there's elasticity in there. It grows and it shrinks with adding and deleting values in there, right? So this is it, except that instead of integers, what we're going to have in there are the terms that belong to our vocabulary. Now going back to hardware, because everything in the end ends up on computers, information is physical. What happens in reality is that in fact, the entire B plus tree is going to be stored on disk. But for efficiency, we load the upper part of the tree to the memory. So it means that the first few levels of the B plus tree, we can do them in memory, which is much, much faster to look up the terms. And then we selectively read from disk. Imagine that I'm looking for something here and I know that I have to read this, then I will only read these from disk, right? And because now the sizes of these leaves are nicely made in such a way that it matches the disk blocks, then we are efficiently using the disk. And what's important is it's a partial read that we do not need to read if what we are looking for is there on the right. So you see how it interfaces with hardware. The upper part is loaded into memory and the lower part stays on disk. Now there are, of course, cases that if you have enough memory, you can fit the entire B plus tree in memory, then you should do it, right? If it's small enough that it fits. And in fact, it's a recent trend in database systems nowadays that people take machines in the cloud with gigantic amounts of RAM, and now they try to fit the entire index in memory and sometimes even the entire data in memory. Of course, it's more costly, and that only works if the data is not too large. All right, but if you want to download the entire internet, then fitting it all in memory might be a bit of a challenge. So then you're back to having to offload some of it to the disk. Any questions on B trees, B plus trees? Who is now comfortable with them? Very good. So now we are equipped with an enhanced structure that organizes our vocabulary in a searchable structure that gives us, in logarithmic time, access to the posting lists associated with any given term, which now allows us to take our system further and support even more queries. And one type of query that people can commonly do, especially think of that use case with a lawyer's office, that they are searching the law and trying to search some data. They might use some joker symbols, like the star symbol. And that is used to match any sequence of characters. Imagine that you're looking for computer, computing, computed, and so on. Then you just write compute, and then a star, and then you catch all of the terms. So that's called a wildcard query. So if you just put a wildcard, then that matches anything, but of course that wouldn't be very useful. It's useful if you put it inside words. For example, you might be looking for Zurich, the English version, or Zurich with the umlaut, or UE with the different conventions. So that you can do like this. Just put a small star instead of the umlaut, right? So you can have multiple spellings like this. Computing, I give you as an example. Now you have informat star, then you catch informatics, information, informative, and so on. So that's it. And so now you see, now the buzzword is prompt engineering and how do you speak to an AI? Back then it was Boolean query engineering. You really had experts that knew how to build their queries using also these extended features to find the information that they are looking for. You can also use multiple wildcards. You can put them in the middle of the words, at the beginning, at the end of words. So that would match, for example, these completely nonsensical strings as well. You can put it at the beginning. That would catch economics, physics, and so on. Math would catch mathematician, mathematics, mathematical. So you get the idea. But now, my question to you is, which one of these two queries do you think would be the easiest to implement given what we now have, including the B+3 organizing the terms in the vocabulary? Is it the first one or the second one that is the easiest? The second one? Who agrees with the second one? Yes, it is indeed the second one. Why is it easier? Mm-hmm. Do you need a B3 or a B+3 for this? B+. Yes, exactly. So now you see why the plus, the premium feature with the highway of that allows you to navigate through the terms is useful. And indeed, the second one is going to be very easy to solve. Here's an example with made up letters in here. And imagine that the query that arrives is BA star. So what I need to do is locate the left and the right of that. So BA would be my lower bound, and BB would be my exclusive upper bound, right? Anything that comes between BA and BB, BA included, BB excluded. So I start from the top, and now I see, okay, the second and third children, I will use them completely, right? But then BA lands somewhere in the middle in here, right? So it's somewhere here. So it means that, no, sorry, I mean in the middle of the second, right? Because it's between AC and BAD. And so that means, and you can visualize it here, this is my frontier. This is where I'm cutting. Anything that is on the left is surely not in my wildcard query. So I locate the BA here, and I can walk all the way BA, and here I stop. And that is using my premium feature highway that allows me to go through the terms. Who understands that? Right? So you locate the lower bound and the upper bound, and then you just navigate using the singly linked list in there. In fact, you don't even need to locate the upper bound. You can just directly have a while loop until you reach it, and you just need to locate the left. Okay, and that's. What did I do with the colors? Probably, yeah, I don't know. I was drinking too much orange juice. So only this. Oh, yes, sorry, that's what I did. I put in yellow because these are the ones we read from the disk. So that we load from the disk. And then we only are actually going to read these that are bold and in green. Who is with me? Very good. And now we access the postings list. And now you see that solves the wildcard query BA star, because now we are going to locate all of the postings of all the terms that are in that interval. So now hopefully you see the pieces of the puzzle that start assembling together with everything we've been doing. The standard inverted index, the B+3 to locate the term, a range of terms that we obtain via a wildcard query with the star at the end, and so on. Okay. How do we deal with star AC? Can we do it efficiently? I see a lot of heads like this. Who thinks we cannot do it efficiently? And you are right, we cannot do it efficiently. In fact, we could do it in linear time, by traversing all of the terms and checking if they end with AC, right? But that's not very efficient. But there is a solution for that. But that solution involves more work. It involves an additional structure. It's always the idea when you have an information retrieval system or a database system, you can always make things faster. But whenever you make things faster, you usually have to pay with space and with time because you need to create an extra structure, an additional index, an additional, right? And then at query time, it will suddenly be faster. But there is a cost in space because you need a place to store that additional structure. And there is a cost in time when you prepare the index prior to the runtime, prior to the query, you need to build these structures. So that's what we are going to do now. We are going to build an extra additional structure. And the way we do that is we take our vocabulary and we write all of them backwards, and then we treat it as if it were the actual terms. And we build again a B plus tree with the mirrored terms. Who agrees that solves our problem? Right? Because now all we need to do is just mirror the query. So now we say CA star, and we look into this additional structure that has the mirrored terms. And then we locate CA and CAB that in fact corresponds to AC and BAC, right? But because of this additional structure, now they are close to each other. All of those that basically correspond to terms that end in AC are close to each other in that new structure, right? And now we can use the postings list that we get from there. Just don't forget, this is not the standard inverted index. This is a modified additional index in which we mirror the terms. Okay, now even harder. How do we solve that one? Any ideas? Imagine we have the structures I introduced to you, the standard one and the mirrored one. Any idea? Yes? Conjunction or disjunction? Conjunction, exactly. That's exactly the idea. You basically separate it into ZU star and star CH. ZU star we solve with the standard inverted index and the premium plus feature. And star CH, we use the mirrored version of the index, also with the premium plus feature. And that's it. And then we get the postings list and we intersect them. And that you know how to do too. You have the algorithm to intersect postings list, right? So we intersect them. That gives us the results. Exactly the results, or potentially not enough results, or potentially too many results. Reformulating, can we have false positives or false negatives? Yes, absolutely. So this is one reason. If you do the intersection at the postings list level, you might end up with documents that contain 2 micron and I don't know, bar, right? So that's the risk if you merge at the postings list level. What that teaches us is we should intersect at the level of the terms and not at the levels of the postings. If I do it at the level of the terms, who agrees that now we have solved the problem and we no longer have false positives for that query right here? Okay, raise hands. What about this one? Who thinks we will not have false positives here? Who thinks we will have false positives? Yeah, can you give me a false positive? A term that would appear but shouldn't? Statics, exactly. Because then you do static star and star ticks, and statics is a false positive. Who sees that? Right? It doesn't match the wildcard query. If you look at the wildcard query, that's not a word that has this pattern. But if we decompose our wildcard query in this way, we have a false positive. Now, of course, false positives are not really that much of a problem. You just do a post selection. You add one more filter after you have done that. It's still going to be faster than if you had to scan via all the terms, right? So, but you always need to ask yourself the question, do I need to add this extra filtering to exclude the false positives or not, right? And that really depends. You need some sort of heuristics in there. So here you can probably, as a rule, check if the left and the right intersect in some way, which is what creates the false positives. If it doesn't, then you know that you can't have them. Who's with me? Very good. Still have a few minutes. So we add a post filtering, and that does the trick. And doing a post filtering after using an index structure is something very commonly done in databases or information retrieval. Totally normal thing to do. Okay. Now I'm going to add yet another structure. So we had the original one, we had the one where we flip and mirror the terms. Now I'm going to be doing what we call a rotation of the terms. So what I do, imagine that you put, like this is plant, imagine that you have a ring, P-L-A-N-T, and then it starts all over. In this ring, you also add a dollar symbol to mark where the word ends, because otherwise you don't know where it ends, right? So dollar, P-L-N-T, and then dollar, P-L-N-T. Imagine this ring. And now you write down all possibilities for fully reading the ring. Then you have dollar plant, T dollar plan, NT dollar pla, ent dollar PL, LANT dollar P, and plant dollar. These are called rotations of my term. So who agrees that I could use this rotation thing, if I would build an additional structure that could index the rotations in the same way I index the mirrored versions of the terms, I index the rotations. Who can tell me how I could use such yet another structure for executing the query that you see on the right here, EL star T? What rotation should I be looking for, or what range of rotations? I'm basically looking for a word that ends with T and starts with PL. Yes? Mm-hmm. So that's exactly the way to start thinking about it. So we have the PL star. So we are going to need a pattern with PL star. And we need something that ends with T. Can you try to merge what you proposed into a single prefix of a rotation? Just one prefix. On Zoom? Anybody on Zoom? No? Let me give it to you, then you tell me if that makes sense. T dollar PL as the lower bound. And all the way to T dollar PM excluded. Who would agree with that? Because T dollar PL whatever basically gives me the words that start with PL and end with T. That's because of the dollar sign, right? If I see T dollar PL whatever, I know it's a rotation of a word that has to end with T and start with PL. Give you time to digest. Who is with me now? Awesome, most of you. T dollar PL. So I can just turn that into a wildcard query, but with the wildcard at the end. These are the ones I can do efficiently, looking for T dollar PL. And that I can do if I have yet another structure that indexes these rotations. If I have an index of these rotations, a B tree that contains every rotation of every term, then all I need to do is look up the range in that additional structure between $T$PL included and $T$PM excluded. All right, and then that brings me back to the plans. So the idea is I compute the rotations of every term that I have in my vocabulary, all of them, and I sort them nicely and I create my structure. Now we could use a small variation because you remember earlier, we go back here, and I asked you about the false positive, right? Where was that? This one, yes. In our first prototype, we added the posting list to all of these structures. So I have the structure with the mirrored terms plus the posting list. But then we saw that would give us Tsumikon and Bach, right? So we should not merge the posting list. So why don't we save some space and do not add the posting list to the additional structure? We only make them point to the terms and not to the posting list. So it means that here, in my additional structure, just going back to it, I'm not going to add posting lists to all of these rotations of all the terms. I'm only making them point back to the term they come from. And what I get is an efficient data structure that, given a specific rotation or prefix of a rotation, can give me all of the terms that match this rotation. And once I have gotten the terms, now I can look them up in the original index. Who agrees? Right? So this is the way to go. So now I'm going to build this huge structure, a B+3, that indexes every rotation of every term. Like this, here I just have 2 terms, but imagine it with 1 million terms. I just have plant and ETH, and that's what I get. It's a B+3 that indexes my rotations. And now if I have, oh, I thought I was giving an example. No, that's something else. Yeah, so that's it. That's called the permuterm index. And the permuterm index allows you to solve queries that have a wildcard in the middle. So wildcard at the end, easy one. Wildcard at the beginning, you mirror. Wildcard in the middle, you could use a conjunctive query with false positive elimination. Or better, you use the permuterm index that directly gives you the terms that match. Let's go to something even more difficult. Star MPU. That I'm going to leave to you as thinking about it for next week. I'm not giving you the solution. There are also solutions that allow us to do that, and just to get more and more difficult. So that's it for today. So thank you very much for attending. I hope you enjoyed it. As always, you're going to have the exercises nicely prepared by the TAs in the sessions. We have a new TA, Severin, who is going to have, I think, group number 3. Group number 1, since it's online, we just changed the room to online, Marcin's group. And anybody who is looking for a group to register in presence can register to group number 3 and join Severin, right? I think it's in HGF 26.5, if I'm correct.
Actually, for today, Severin will take over Kumar's exercise session. Like the secretary allocates the room and try to do it.
Okay, yeah, thank you. So basically what I said, only from next week. For now, as for today, as planned before. Thank you very much, Georges, for this. So thank you, Georges, for moderating today's session. And I'll see you next week at 10 a.m. Thank you, everybody.